Hello and welcome. This video we're going to discuss three dimensions, three-dimensional equilibrium problems. So we have um, this item which is supposed to resemble a street light or a street post with lights hanging off. First of all, we're going to ignore the posts and we're going to focus on the weights of these traffic lights. And we want to figure out the force and moment about this. I'm going to solve it in a general way, but then I want you to notice that um, all the forces are in parallel, which actually will dictate, and it will show when all the forces are parallel, you can generalize to only solve for a couple of equations. But let's start with the general equations and start with our givens. So come over here. We're going to choose a pencil, and we're going to choose black, which is awesome. And what we can do here is say, well, we're given a couple of things. One thing is we're given the weight of each one, and we're going to call this weight of A and the weight of B. We could say that the weight of A is equal to the weight of B, which therefore equals the weight. So with that, we know that. And we also know we could say A and B is known, and also C. Now we can put values in there, but we're going to keep it general for now. You can always put values in, and these A's represent displacement and or distance, and this W represents the weight. And of course, in most standard things, our gravity is going to go in the negative z direction. So what are we trying to find? Let's pinpoint this, and we're trying to find the force at O and the moment at O. So there is a reactions going on. And we'll draw a free body diagram and we'll eliminate some things, but that's what we're looking for. First, let's look at the free body diagram of this. So free body diagram of this street lamp of item. So we can say, well, we can put a little rod here. We can put a little rod going this way. And we can put another log perpendicular. Looks like this. Now that's not it, that's the start of it. And then we're going to put, I'm going to start to make these all colorful. So we have two applied loads, and the two applied loads, one on this side, and we're going to make that vertical. And that will give a weight. Just call it W, or we can call it WB, because this is point B. And we can say that this is A, and we have a WA here. So if you notice, the weight is the same, but we're only saying that it's W. What I'm going to do is I'm going to say that they're both vectors. And they're going in the negative z directions, but the weight is going to be W. And again, it could be 200 pounds. It could be 400 newtons. Whatever it is, that's what we got. We can also, what we also want to do with our free body diagram is put in our coordinates. Our coordinates for this problem are already given to us, which actually simplify the problem tremendously. And if you notice a couple things, one thing is these are the only applied loads, and they are parallel to each other, which we'll take into account when we look at and try to simplify this problem. Furthermore, let's look at the reactionary loads. So we have a force vector and also a moment vector, and that's what we're looking for. So let's start. And we're going to start by the general equations. So we're going to put a solution here, and we're going to start by the general equations. And what we can do is we're going to, equations. So what we can do is we can say the sum of the force vectors now is equal to 0. That's what we can say. That is the most general equation in statics. That one and the sum of the moment vectors is equal to 0. We can do this in 3D. So we can say that, all right, well, we only have one force. We have Fox, and that's the only thing in the I direction, plus Foy, only thing in the J direction. Oops, I don't know why I put the J there. J goes out here. And then we have the force of OZ minus the weight of these two. So again, these are the only things, and we can simplify that, and we can say the weight minus another weight. And that is in the K. All of that gets equal to 0. So right off the bat, we know that this force of X is 0. This force of Y is 0. So now that's saying that the force of OZ is equal to 2W. And if you want to put it in vector form, that is in the K. Oops, nope, that's not vector form. That's the component. But if you wanted to put it in vector form, that force of O in vector is equal to 2W K. And that's the direction. So it's going to be pointing straight up. Now this, again, you can simplify this by saying and just looking and observing that these forces are in parallel. And if all the reactions are in parallel, I mean all the applied loads are in parallel, the reactions have to be in parallel as well. So you can simplify it down to one force equation. And if that's the case, you'll notice another trend when we take the moment. So if we look at, we further on down, so we solve this, right? And that's solved. But we want to take a look at the moment. So we take the sum of the moments vectors is equal to 0. So we have one moment here. So we have the moment about O, and that's in a reaction, plus, now here's where it gets sometimes gets a little tricky. We're going to change this to green. We're going to say that this from there to there is R vector OB. All right, from O to A, that's R vector OA. Remember that if you look up top, you'll notice that this is the A, this is B, and the height of this is C, which plays into an important role. But we're still in kind of general equations, so we're one step beyond general equations, and we can say that ROA, the vector ROA, cross product with the WA vector plus ROB vector cross with WB vector, all that gets equal to 0. So let's draw on a side now. And let's take a look at what occurred. Or let's take a look and define all of these. So we can say that ROA vector, if you look at this, it's going positive X, and that's in the A direction, so it's AI. There's nothing in the J, and it goes up C in the K direction. All right, so that's all. Then we have WA vector, and we get a negative W in the K direction. Similarly, we can say that if we look at the ROB vector, it goes positive B in the first of all, there's no component in the I direction for ROB vector. But then it goes in the J direction, it goes B in the J plus C in the K. ROB and ROA had the same height. We can that's what we said before, or that was the defining of the problem. we keep going and we can say that the WB is equal to negative WK. That's it. I mean, both of them have the same vector and they are in parallel. Boom and boom. They are the same. Interesting. But they are not in the same, they do not lie in the same plane. The rectangular coordinate system plane, x1 lies in the xz plane, the other one lies in the yz plane. So that comes into important when we're talking about moments. So we're going to expand upon this. And we're going to say that that is equal to, and we're going to put our determinant here. This is a good way to think about this. And we can say, but then you put the R value here, which in this case it's A, 0, and C. And then the W, or the force, is 0, 0, negative W. So if you work this out, here's what you're going to get. You're going to get, first of all, it's going to be in the J direction, because it's going to be an I cross a K. I cross a K is a negative, so it's a double negative, so we actually have A, W, J. That is the moment, the applied moment, caused by this moment A. And if you notice, if you try to rotate this and cross, you're going to get this moment about the Y, and it's going to be a positive if you do the right-hand rule. Next, similarly, we can say that, go down here, we can still say the same thing, say that I, J, and K, right? And then we can go, what's ROB, which that's 0, and that's B in the J, and C in the K, and again, we can similarly with this is 0, 0, and negative W. So what does that turn out to be? It's a J cross a K, so you know you're going to get an I. And anytime you cross a J times a K, you're going to get a positive. But in this case, we have a negative W, so it's going to be negative B W in the I. So let's take a look at what that looks like. So we're crossing R with B, so visually it looks like this, right? So if you look at it, it's going in that kind of direction, and it's going to negative X direction or negative I direction. And that's what we have. So that's good. But if you notice, we did that. We have no K's. No K direction. Therefore, if we look at this, no applied force is causing this to rotate about this, because all the weight or all the forces are parallel to this Z axis, and that's good for us, so we can eliminate that. So when we're doing this, when we know everything's in parallel, all the applied loads are in parallel, we can say the other two axes would be the only other equations we would use. So some of the moments about X would equal to be 0, and some of the moments about Y is equal to 0. So those are the two equations if you wanted to do this more succinctly. Sometimes it's not good to do that in shortcut. Mainly you have to earn your right to these shortcuts. So if we collect all of the terms, we can say that the moment vector O is going to be equal to BW in the I minus AW in the J. You see, you have to have counteracting. That's why the signs change. You have to counteract the moment about this O position. So that would be your second answer. And again, you can simplify this, but I wouldn't simplify it at first. This is I'd get used to using these general equations first, the sum of the force vectors, sum of the moment vectors in 3D, and then only when you start to recognize this, you would use some of the shortcuts. So have a great day. Keep learning.